Hi, I'm Donna Pearson from the National Research Center for Career and Technical Education, and it's my pleasure to present to you this series of videos on Math-in-CTE. We receive requests daily from teachers and administrators around the country wanting to know how the Math-in-CTE model works in real classrooms with real teachers. And these 3 videos that we are presenting offer you the opportunity to see a variety of teachers teaching a variety of CTE content using the Math-in-CTE model. If you haven't already done so, you might want to take a look at the materials that are on our website at NRCCTE.org, and you might also want to view the fuller video on the Math-in-CTE model. Essentially, the 7 elements offers the teacher a framework by which to develop a lesson and to teach a lesson, and this framework in its 7 elements offers an opportunity for a transfer of learning from the math that's embedded naturally in CTE to the explicit mathematics. And in this way, students are able to understand mathematics and learn it contextually. In each of these lessons, the instructors have used a 7-element lesson plan to guide their instruction. However, I'm going to point out and highlight the elements that they have used particularly effectively for these demonstrations. I hope you enjoy the videos. The lesson that you are about to see is a lesson from aviation called Weight and Balance. One of the hallmarks of a Math-in-CTE lesson is that it always situates the learning in the CTE context. In the video that you're about to see, Mr. Parry from Arlington Career Center is going to teach a weight and balance lesson. And as he begins this lesson, please notice how he does not introduce it as math, but he introduces it in the interest of the students. He very clearly grabs their attention and uses an introductory activity to get their minds set on the math that is ahead.
In today's lesson, we're going to be discussing weight and balance and the importance of weight and balance in making sure your airplane is safe to fly. I have to present to the students, or I have presented to the students in the past, some of the initial information about the datum planes and why we use datum plane in the design of aircraft, and why we have to calculate the weight of the airplane. When you design an airplane, it can only lift so much. The lift is provided by the Bernoulli effect on the wing, and therefore we need to design a wing to carry so much weight. So we need to know the weight that we're going to go to. Well, if the student overloads the airplane, then the airplane will not lift off because it can't provide enough lift to get the airplane off the ground. If the balance is not correct and we put too much weight in the front of the airplane, it's like a seesaw. You won't be able to raise the nose off the ground and get it off the ground. If we have too much weight too far back in the airplane, it's like the other side of the seesaw. The airplane will lift off, but then it may continue to rotate up and stall and crash. So making sure that the airplane is within its limits as designed by the aircraft designers, and the weight is less than it's supposed to be, the airplane should fly correctly. Today we're going to be focusing on weight and balance of an airplane and the importance of weight and balance in an airplane. There's no sense having an airplane that can lift 2,400 pounds and then try to have 3,500 pounds in it. It won't fly. We've studied the fact that we design an airplane based on a certain characteristics we want it to have to carry a certain weight, and if you exceed that weight, it will not get off the ground. I'd like to do a little demo of that right now, and if my 2 students will come forward, Miggy and Zach. If you want to think of Miggy as my airplane, he has a certain capability. He has a certain capability to perform on his thing. We designed him a certain way, and he's going to be able to lift so much weight with his wings, if you want to think of him as the wings. Go ahead and stand close and lift that up. Okay? He obviously can carry this much weight. Give him some more books there, Zach. Okay? He obviously can lift that much weight. Give him some more books. We're going to get to a point eventually where he can't lift the weight of books that we've given him. We just reached that point. An airplane is exactly the same way. it will get to a point where it cannot lift off the ground because there's too much weight on it. Shift some books back. Let's give them only a 4 this time. Okay, now, I'm going to have Miggy step back about 6 to 8 inches away from there. That's a little too much. Come a little farther forward. There we go. Right, 6 to 8 inches from where he was before. And now he's going to have to bend over to pick up the books. Let's see if he can pick up just 4 books. He can't pick up the 4 books. Because why? His center of gravity is too far back, and as a result, he's out of balance and cannot lift the books up off the desk. Now, you saw before when he was close, he could lift the weight, but now we also have to take into account on an airplane the balance that we have to carry. Thank you very much, Zach and Miggy. Appreciate it. So, we have to make sure that we know what the airplane can carry. We have to know that the airplane weight is within limits. And how do we make sure it's able to get off the ground? We do a bunch of calculations beforehand called weight and balance. And we're going to go through this today to make sure that you understand weight and balance. Let's take a look at an example of what we're going to talk about when we talk about weight and balance. Okay, here we have, obviously, a young man by the name of Angus. He's at the diving board at his local pool. He weighs about 150 pounds, and he's going to come out here 10 feet. And this distance from where he starts to here is 10 feet. And he's going to come out 10 feet, and he weighs 150 pounds. Okay? When he's come out that 10 feet, what's happened to the board? It bends, because now instead of the weight being supported back here, the weight is now out here and still being supported through that 10 feet. So this is what we call moment arm calculations, and we're going to demonstrate that by the fact that now we're going to take that 150 pounds and move it through 10 feet. And that gives us a moment arm, or a bending motion in this direction, clockwise. Clockwise is positive. Bending motion is thing of 1,500 foot-pounds. Okay? Now, if this board is not designed to take 1,500 pounds of moment on it, what's going to happen to it? It's going to break, and he's going to fall down. The same thing happens in an airplane. We have to make sure the airplane is designed to carry the weight wherever we put it in the airplane. Now, we can't just put it anywhere. It has to go in certain locations. So when we design an airplane, first thing the designer does is start with a datum line, or a reference datum line. And now we're going to use everything that we measure from that point of where the weight is. And so we're going to take a look at this weight, and we're going to say that this engine, here's a nice red engine there for you, and that red engine happens to be let's make it 50 inches back, and let's say the engine weighs 400 pounds. Okay? So we would do the calculation from this datum line that this weight is out 50 inches, is out 50 inches, and through 400 pounds. And we would multiply that out, 50 times 400 times 400 equals 20,000 inch-pounds. Okay? Now, we also want to have other people on the airplane, other cargo on the airplane, and so we need to actually go through the entire airplane to figure out where the weight is so that we can calculate out where all the weight could be centered, and that's what we call center of gravity. Center of gravity. So this is where we want to take and put all that weight through, is that center of gravity, and figure out where that is. Because when a designer designed the airplane, he's going to take into account all this normal information we have here and make the center of pressure, of lift, as we've talked about, and the center of gravity inside of a box. So we have to know how to do that particular problem.
At this point in the lesson, please notice how Mr. Parry begins now to address elements 3, 4, and 5, the transfer of learning. He begins to explain the math that's embedded in a weight and balance lesson, and then he gradually walks it across to the explicit mathematics that they might see in a math classroom.
So if you'll turn to page 8-36, please, in your textbooks. Okay? We're going to take a look at the first problem there on the bottom of page 8-36. 8-36, and see how it looks when we do it in writing. How we do this when we do it in writing. Okay, so we're going to take the weights, we're going to take the arm, and we're going to take the moment to create the moment for that weight. Now, the empty weight of the airplane in this case is 1,150 pounds. The arm is 70 inches. And you would multiply those two numbers together to get 80,500 inch-pounds. Inch-pounds. The pilot, who weighs 135 today, and is sitting in his seat at 73 inches back, because now when we multiply 135 times 73, you're going to come out with a number like 9,855. Okay? So we're going to total up the weight now. How much weight do we have on this airplane with the pilot on board? We have 1,285 pounds of weight. We don't care where the inches is yet, because that's what we're going to calculate out down here at the bottom when we go for the center of gravity. The moment turns out to be 80,500 pounds, and we total up 90,355 pounds, the same information you saw in that book on page 836. How do we calculate where the center of gravity is? Well, we're going to take a look at center of gravity, and we're going to take that total moment number here, and we're going to divide that by the weight of 1285. And when you do the calculation, it comes out to be 70.3 inches. Is that within limits? Well, the next step would be to check and look at what the book has told us. If you recall back here, I told you that the designers have figured out where that center of gravity needs to be. If the center of gravity is too far forward, like in Miggy's case when he tried to lift the books, the nose of the airplane will stay on the ground because you won't have enough ability to pull it up in the air. If the CG is too far aft, back here somewhere, then when the airplane rotates, it's going to continue to rotate because the aft is too heavy, and it's going to fall to the ground and stall the airplane. So we want to make sure that we can do these calculations to know whether the airplane is in limits. So let's work through an example that you see in the book, okay? And make sure we know how to do this. So I've taken and reproduced up here the piece of paper that you see in the middle of 838 for doing these calculations, and you can join me in doing the calculations or just watch in the book as we do it. But basically, we're going to take and multiply all these numbers out and then figure out where the CG is and see if it's in limits. Okay? So we're going to take the first one. The plane weighs 1,432 pounds. How do we know that? Every 2 years, every airplane is weighed on a set of scales, and we actually do the calculation of empty of where the CG is, knowing where we calculate all the weights through that. That's an engineer's job, not our job. So we trust the engineers do that correctly for us. And we come up with a number of 53,843 in a moment arm. That's inch-pounds. Okay, in our case today, the pilot, who weighs 145 pounds, is sitting at the 37-inch point in this particular airplane. That gives him a moment arm of 5,365. I don't want to get my numbers wrong, that's why I keep referring to my chart here. Okay, on the front seat passenger, I have my friend with me today flying. He's a light young man, but he weighs 124 pounds, and he's sitting in the same spot in the airplane that I am at 37 inches. So his moment arm is 4,588. In the rear seat passenger, I've decided to take Henry along with me today. He weighs about 180 pounds, and he's sitting in the back. He's sitting about almost 30-some inches behind me, 36 inches behind me. So he's got a little leg room back there. But when I take and multiply 180 times 73, I'm going to get a very huge number. In this case, it turns out to be 13,140. See how much, even though these two weights are higher, this number, because it's so far back in the airplane, outweighs it by 4,000 pounds, inch-pounds, 4,000 inch-pounds, because he's further back in the airplane. We got 78 pounds of bag, Henry. You can't take that much to Bucknell with you, sorry. Can't take that much to Bucknell. But that's even further back. That's another 18 inches further back behind Henry. So we got to multiply those two numbers out, and we get the number of 7,410. And then fuel. Oh, did you want to fly somewhere today, Drew? You do. We better have some fuel on board, shouldn't we? This is 50 gallons of fuel. Fuel weighs 6 pounds per gallon. So we multiplied those two numbers out. Our wing tanks, where we're going to put the fuel, are located at 46 inches behind that datum line. And so we multiply those two numbers together and get 13,800. And again, this problem is, if you're following along in the books, you can see it's all in the book. Hopefully the same numbers are appearing there. Now, the next thing we do is we add the weight up. Because the first thing we want to do is make sure we're underneath the weight that the airplane can lift. So we're going to take and add this up. That's 7, 11, and 8 is 9. I'll write the same color, I'm sorry. 9 carry a 1. We got 8, 10, 18, 25, 25. Looks about right for that number. Carry a 2 up here. 16, 17, 18, 19. 19 and 3 is 22. So we have a total weight of 2259. If you look at your center of gravity chart, you'll see the fact that we can go all the way to 2,500 pounds. So we have less weight than the airplane can totally lift. Again, we don't care about the arm now. We're going to calculate that because that number is going to come out down here when we finish with it. Now, I'm not going to do this one in my head, folks. I'm just going to copy down the answer for you. This turns out to be 98,146 inch pounds. Okay, so where's the CG? Okay, we're going to take that 98,146 and we're going to divide it by the weight of the airplane, 2259, I'm sorry, 2259, and find out that the CG is 43.5 inches. And the answer would be in inches because we need to do that. Now, we'd go to the CG chart, and William is 43.5 inside normal limits for 2,259 pounds. Yes, it is. So, we are legal to fly. Henry will get to take the 78 pounds of useless junk with him. Henry can sit in the back seat. I've got my young man with me at 124 pounds in the front seat, and we can legally fly from Manassas to Bucknell, Lewisburg, Pennsylvania, and hopefully not crash if Mr. Parry flies it well. So we're going to do that. So that's how you do weight and balance. Now, pretty straightforward work what we do here. I've prepared another example for you to try out on your own to see how you would calculate out the weight and balance of that. This is located on the Section 4 problem that I would like you to do now, please, and see what answers you come up with for this particular problem. In this case, we have a family of 4, husband, wife, and 2 children, and they're flying to Disney World. And so I've asked them all their weights. I've put down the numbers for you that we're going to use to multiply with the arms in there. And I would like you to calculate the total weight for the airplane as well as the moment arm and then determine the CG, just like I did. The answer that I got and the textbook got was 43.9 something or other, 43.9. Again, we would go back. Are we underneath our weight limits? And yes, we're less than 2,500 pounds. Are we in the CG normal operating range? Yes, we are. So this family of 4 could go to Disney World with that information. And that's mainly because the 2 children in the back are very light. So that's why we can afford to have 150 pounds of baggage in the baggage area, because the 2 children in the back seats are very light. So we can do that. So that's what we see here at Career and Technical Education side of the house. Now, what does this look like if you were back in your math class at your home school doing this? If you look at Section 5 on your sheet of paper I just handed out to you, I've given you a little equation problem to solve. I want you to determine the average cost of each item. How many items do I get, and what is my average cost for that list of items?
One of the wonderful features of the Math-in-CTE framework is that it offers opportunity at the end of the lesson for students to demonstrate what they know and are able to do. And in this tape, you saw how Mr. Parry used authentic assessment from the FAA exams to practice the students and offer them the opportunity to tell him what they knew about aviation. This was in preparation, by the way, for an FAA exam that was coming up later on in their course.
So obviously, just like we did on the weight and balance, we're going to take and do the calculations for that. And if you'll go ahead and do that problem, I'll come around and check that one, see what this would look like in your math class at your home school. 2 answers I'm looking for would be the total spent and the number of objects, and then obviously the average cost per object. We've stated that this is a lot like the math problem that you might have at your home school, doing an average cost analysis of the cost of objects. Now I want you to turn the page over, and this is a real problem from the FAA test. This is a real problem right out of the FAA test. This is what you would see exactly in the FAA test if you take it later this year. This is one of the actual problems. And what I want you to do is you calculate the information, using the information I've given you on that problem, to go ahead and solve it. And then tell me where the CG is located, and then answer which answer, A, B, or C, is the correct answer. Again, this is weight and balance is a critical issue for flying airplanes. The airplane must be underneath the weight it's designed to carry, and the airplane must be within balance. If it's not within balance, you will not have the controls needed to fly it, or you may stall the airplane and fall out of the skies. You need to make sure that when you do every flight that you do, if there's any doubt that you're within limits, you should do it. Mr. Parry admits that when he goes out to fly, he doesn't, and he's up by himself, he doesn't check it. He knows that weight and balance is in limits. But if I was taking my family along with baggage especially, I would run all these calculations you just saw to make sure I'm within limits. Any questions? Thank you very much. Appreciate it.
I would like to thank you for your interest in Math-in-CTE. If you have more questions, we invite you to visit our website at nrccte.org. Thank you.